Hello? Okay, alright, good. Shalom. Konnichiwa. Hola. Ni hao. ¿Cómo está usted? ¿Está muy bien?
Yes.
Sí.
I was just going.
Did I miss anyone? Okay, yeah, okay, good. Antiderivatives and differential equations. So basically, it's the opposite of a derivative. So this time we're going to start with a derivative and go back to the function.
Nice.
That's what we're doing. So all this time we've been actually starting at the function, going to the derivative, and now this one's going from the derivative to the function. But there's other applications that go with this. Function f is called an antiderivative. It is commonly referred to with a capital letter. The capital letter f is my function. The function f, if capital F prime of x equals to f of x, f prime of x equal to f of x in all the domain of f. Did that make sense? Not really, right? Okay, so basically, if there exists, it has to be continuous, and there's going to be some number right there. Okay, so when I take a derivative of the number 5, what happens to that number 5?
0.
That goes 0, right? And so we need to account for that. So when I take a derivative of something, okay, the 5 goes away, right? But then when I take the antiderivative, I need to account for that number that used to be there. And we call that one c. So it's plus c on that one. So it's going to be adding c to this. So in plus, because we didn't know if there was no number there, if there's no number there, we didn't know that there was a number there already starting out that we need to account for. If we take, again, think about it. If you take the derivative 5, you get 0, right?
Mm-hmm.
So if there's nothing there and we take the antiderivative of that, I need to somehow come up with 5.
Yeah.
But there is nothing there showing that there was anything. So we account for that when we take the antiderivative as saying there is a c there. There was some constant that was there.
Okay, it makes sense.
Okay, there was some constant that was there. Function f, antiderivative, function defined interval I. Any other antiderivative has the form capital F of x plus c, where c is a arbitrary constant. There was some constant that was there.
Is it this, so this thing is about like how to find our function if we know the derivative of this function?
Yes, and we're going to get the whole function at the end of this lesson, because you're going to end up finding a particular solution to the equation. So you're going to actually solve for c also. I want to be free. All right, okay. Antiderivative of f. So, again, accounting for that. So this is going to be what?
I mean, any constant number, c.
C.
Oh, we just write c.
Now, next thing. Remember when we take the derivative, I have the circle thing, right? So we have sine, cosine, negative sine, and negative cosine, right? When I take the derivative, which direction do I go? Clockwise. So antiderivative would be counterclockwise. So now we go this way now. We go counterclockwise. So if I'm taking the antiderivative of negative sine, what's my answer going to be? Cosine theta. Say it again.
Plus c.
Plus c. So it's going to be cosine theta plus c.
So we'll basically add c everywhere. I mean, it can be everywhere.
Okay, yeah. It could be anywhere. But that's when we talk about anywhere, when we graph anywhere, that's called the slope field. We'll eventually get to that. Okay?
Wait. Why are we? Yeah, the plus c.
Because there may or may not be a constant there. So the plus c is just to account for that missing constant. And that may or may not be there.
Even if you don't know if it is?
Okay, yeah. So that's why we use c as some arbitrary constant.
Okay. I get okay.
Okay, so now, here, we're gonna work this, and I'm gonna explain it in a different way, and so I'm gonna say, okay, what would be the derivative? What would be the derivative of cosine theta plus 2?
Negative sine theta plus 0? Or negative sine
Yeah,
theta, basically.
yeah. So it's gonna be, so the derivative would be negative sine theta, right?
Yeah.
Okay, so the derivative would be negative sine theta. But now, if I want to take the antiderivative to go from this back up to this, so I do an integration or antiderivative going this way to get to there, and then I take the derivative to go to there.
Okay.
So I have to somehow account for that 2 that used to be there. It's not always saying that there was some constant. I just need to account for a constant that could be there.
Okay.
Make sense?
Yeah.
Okay, good. All right. Okay, this one over here.
Doesn't really.
This is one of my favorite.
We need to rewrite it.
Not really.
But it's not like.
Yes, it is. It's always right. Now, for this problem right here, okay, what do you do when you take the derivative of x?
How you multiply
The
times
power
the
goes.
Power goes where?
-1.
-1. So if I do the
So
antiderivative,
we have to do the +1,
it would be +1, right?
but there's supposed to be a number before.
Okay. Watch. Okay, so we're gonna start with, and you guys are gonna help me with this. Okay, so this is going to be a good learning experience on this one right here. So I'm gonna start by getting a problem, and we're gonna take the derivative of it. Okay, so I'm gonna make up a different one, then we're gonna come back to this one. All right. So I'm gonna say that I have 3x squared. So take the derivative of that.
6x.
6x, right?
Yes.
So we subtracted 1, right? So what am I going to do to go from here back to here to get this here?
We need to get.
Hold on 1 second. Let me. All right. So this is where we're going to make rules out of this.
So we need to.
Okay. So what's going to happen right here?
Need to like power to +1.
Okay. So add 1 to the power, right?
Yeah.
And then divide by it.
Okay.
Divide by the same.
Then
Divide by this one.
and then divide by the power, right?
Yeah.
So if I do that, it's going to be 6x, right? And so therefore it'd be 2, right? Over 2, wouldn't it?
Yeah.
Because I'm going to divide by that power that I have there now, right? And so because of that, will that give me my 3x squared again?
Yeah.
Yeah, that gives it 3x squared. So have I actually figured out a step for this, right?
Yeah.
So I'm adding to my power, right?
And dividing.
And dividing by that power. Okay. So let's go back and actually do this next one now. All right, so I have x to the 1/2. So x to the 1/2. So what am I going to do to the power?
3 over 2, so it's gonna be.
There's 2 of them there. Okay.
2 of them.
Okay, so you're adding 1 to the power, right? But since it's a fraction, what am I adding here?
2 over 2.
2 over 2. So I'm plus 2 over 2, right? Which is going to give me what?
3.
Okay, so that's 3 over 2. And what am I doing with that 3 over 2? What did I say to do?
Divide.
Divide it by it, right? So it's going to be, this is going to be divided by 3 over 2, right? But since I'm dividing by 3 over 2, I'm going to have a fraction over a fraction. I don't like that.
Multiply.
multiply by the
Reciprocal?
reciprocal of the bottom. Reciprocal of the bottom. So the fraction I just did, I'm gonna reciprocal that one. So this is now going to be, so 2 over 3, right? Then I have x to the 3 halves, and then,
That's it.
nope.
Plus C.
Plus C. Oh,
There we go, yeah. Gotta sprinkle that crap everywhere.
okay.
The plus C is actually gonna indicate all the time that I did the
Yeah,
antiderivative.
but
Yes.
is it
Um,
possible?
Could you put the 2/3 in front of the x instead of putting the x on
Yeah.
top of the?
Yeah, you can.
It will look pretty.
But I like having it in the numerator all the time, because if it's in the numerator, especially if I get some negative off of it, okay, if I have a negative, I need to consciously know that piece is on the top, and if it is a negative exponent, I move it to the bottom later on, okay, to make the exponent positive. And what was your question?
Is it possible somehow to indicate what is C?
Yes, like I said, at the end of this lesson, we're doing that. We're finding a particular solution for this. All right, so see all these things?
Oh wow, it's a table of all antiderivatives.
Yes, table of antiderivatives.
Wait, it's
I appreciate this. Wait, what's the bottom, the sign?
Which one?
X.
H of x.
What's H?
I
Oh, you do.
don't know. I haven't had enough coffee yet.
You want me to go make you one?
I know we're gonna have it here. You guys actually don't get into it, but BC will
Okay,
at the end.
okay.
So,
Wait, what is sine H and cosine?
man,
I know you just.
you know we just said.
But just say what is that. Okay, without. Please. Thank you. Why am I-
Make sure you back up the video.
It's like
All right,
square.
so sum and difference rule. Okay, sum and difference rule. Antiderivative of sum of two functions equal the sum of the antiderivative of the functions. Antiderivative of a number times a function equals the number times antiderivative of the function. So what that says is pull out your constant number. Factor it out first. Okay, right here. If k is a real number and f is the antiderivative of f, then kf is the antiderivative of k little f, right? Because f is my function, right? It just basically the number that was out front. You could factor it out, take the antiderivative, and then multiply it back in. It happens a lot when we have pi. You don't actually have to have pi in my equation. I could just factor it out first, and then when I'm done, I multiply the pi back in. That's basically what we're doing with the whole thing. Because pi makes a lot of the problems complicated because they give you a whole bunch of decimals and stuff. So we just try and take it out and work on it later. All right, find the antiderivative of this. So let's start with, so it's going to be capital F, right, of x is equal to, hey, you guys, what is the derivative of e to the x?
E to the x.
So my answer for e to the x antiderivative would be?
E to the x.
There we go, e to the x, hold it, keep going,
No, plus E to the x.
plus what?
Plus
2x.
3x.
2x to the third power.
No wait. It's gonna be.
Is it 2 or 3?
2x to the
I know
third
it's going to
power.
be plus and it's x to the third, right? Let's write the variable first.
It's 2.
2.
So it should be 6 over 3, right?
Yeah.
6 over 3 is going to give me 2, right? And this is going to be, so if it's that negative sign, that becomes
Plus cosine.
plus cosine. So it's going to be plus cosine of x
Plus
and
Plus C.
plus c. There we go.
We did it.
Yeah, it's actually not that bad.
Yeah.
Okay, well, once you guys figure out the little tricks to this, this actually comes out pretty simple.
It's like anti-voodoo magic.
Okay, yes, anti-voodoo magic. It is. what's the opposite of that? Anyway, equation of the form dy dx equals f of x, example, a differential equation. For this solution of this differential equation, a general solution of the differential equation consists of all the antiderivatives of f. Okay, this one right here. The general solution is the one that says plus c. Okay? That's the one plus c. Then the bounded condition, initial condition used to conjunction with the general solution to find particular solution of the differential equation. So, what that means is we're going to figure out what c is. Okay? We're going to figure out what c is, but c could be all kinds of things. But we're going to find one of them. It's kind of like the tangent of a line, right? And you know the tangent of a curved line, that changes all the time, right? It changes for every x, doesn't it? Say yes.
Yeah.
Same thing goes for the particular solution. So depending on what my x value would be, my solution for c could be different also. Does that make sense? So I could actually have a bunch of different values for c, but I'm just finding one of them. That's why it is a particular solution. All right, so solve right here with the boundary condition when x is 3, y is -1. Verify the solution. Okay, so let's start by taking the antiderivative. Okay, so the antiderivative would be, let's say, so if it's dy dx, I'm going to come up with y equals, what's my variable? If you do the variable first, it makes it easier. So it's x to the third over 3. Like I said, it's easier if you do the variable first. Okay? Plus, and this next one's going to be
X to this
x squared, right?
X squared
Over,
2,
which just gives me
1.
1, right? So it's just x squared, right? Okay. And then right here, this plus 1
It's X.
plus 1x, right? Because I'm adding 1x, right? I'm adding 1. There is no x there, but it gets 1x because I have to add it, right? And therefore, from there, it's going to be plus c. Plus c. So now we're going to solve the particular solution when x is 3, y is -1. If you look at this function right here, I have 3 variables, don't I? I have an x, y, and a c. If I know what x and y is, can I solve for my last one, my c? Yeah, algebra. So I'm going to solve for c because I'm given the x and the y now. So let's go ahead and do that. So it's going to be -1 equals 3 to the third over 3 plus 3 squared plus 3 plus c. So 3 to the third is going to be 27 over 3, which is 9 plus 9 plus 3 plus c is equal to -1. So that is going to be 1821. So it's going to be 21 dang it. I was even thinking it. -1. There we go. Okay. So subtract 21 from both sides, right? So my c is -22. So my one particular solution for this one is going to come out to be y equals x cubed over 3 plus x squared plus x, and then it's going to be minus 22. There we go. That's not bad, right?
Yeah.
It's not bad. Okay, I think we are going to do more of this.
That is only 2.
Crap, no, because... Okay, so yeah, I have to finish this one. Differential equation involves a higher order derivatives. For example, the second derivative, so it's going to be d squared y over dx squared. So that says it's the second derivative of this. Example, a second order differential equation. The order of differential equation is the order of the highest order derivative of y appearing in the equation. Does that make sense? Probably not, right? So let's actually, okay. So what did I call this? It's the second derivative, right? Okay. With the boundary conditions when x is 0, y is 1, and when x is 3, y is 8. Verify the solution. Okay, so let's start off with this. So let's go ahead, and I'm going to start off with my first one, which is going to be dy. So I'm actually doing the first antiderivative, right?
Yeah.
So it goes from second to the first, right? Dx is equal to 4x cubed plus c. Now, what did I say? I said I had a value, right? Okay, so let's go ahead. So it's going to be x is 0, y is 1. Okay, so it's going to be,
How we can plug it in here?
Wait.
We know y not divide over dx.
then,
Yeah, but it's y. not
and when here. Okay, so we're plugged in there. And if I were to do it again, I would get y equals,
We're finding the
X to the
next
fourth.
one.
so it's going to be x to the fourth
plus cx
plus cx
plus c.
plus c, and this would be like a second one.
Wait,
Okay.
they're different.
Because we had a particular solution in the first place, right?
Okay.
And then we have another particular solution.
Oh.
So how we gonna find if there's
So from the first one, I'm going to actually plug in the information given. So the first set. So the first set is 0 and 1, right? So if I plug in 0 and 1,
c is gonna be 1.
c is going to be 1, right? This right here. So if x is 0, this is going to be c is 1. So we're going to get c equals 1. So in this case right here, I can now change that to now this is 1, right? And so when I actually plug it in again, where x is 3 and y is 8, so this is going to be 8 equals x is 3, so that's going to be 81 plus 3 plus c, whatever my second c is, right? So that's going to give me 84. 8 minus 84 is
Negative 76.
-76. So I have the two solutions right now. So my first function, the function, as I actually go all the way to do this, is going to be y equals, so the function for this one right here specifically is going to be x to the fourth plus x minus 76. So we plugged into the first one, right? Oh, I'm sorry, up higher. So we plugged into the first one. We got the first particular solution off of it, and then we plugged into the second one, which actually goes to the first derivative and then back to the function to get the original right here. So it's basically, if I'm talking about this in terms of physics, I'm starting with acceleration. So this would be acceleration. So if I take the antiderivative of acceleration, I would get velocity. And if I take the antiderivative of velocity, I should get,
Delta x.
which would be
Displacement.
position. It's going to be position there. Okay? All right. So let's take a look. I think I'm trying to make sure. Yes, that was it. All right, tomorrow I'm going to give you guys more time to work on this. I'm going to have another set of homework though.